heard the sound. Okay. So I'm going to start with a totally, well, I'm going to start with a couple of minutes discussing what the course is about in vague terms, and then we're going to start in on the beginning. So this is a 2-semester sequence that, with broken chalk, covers linear algebra and multivariable calculus in an integrated fashion. So the theme here is that if you go back to the beginnings of calculus, remember that? What's the derivative about? You have a function that's differentiable. What's the meaning of the derivative of that function? Instantaneous rate of change. Anything else?
Slope of the tangent line.
Slope of the tangent. So I like that. What is the importance of the tangent line?
It only touches the graph one place.
No, I don't like that, because it's not true.
Oh.
What's the importance of the tangent line?
There's only one?
It shows the rate of change at that specific point.
Shows the rate of change infinitesimally at that point. I mean, Philip, so I could take a different one and still have it be only one. But of all lines that you could draw,
It approximates the graph exactly at that point.
not exactly, but it's the best linear approximation you can have. I think the class list needs to come back over here.
Does anyone need this?
So the tangent line is the best linear approximation to the function at the point x equals a. So if we want to talk about calculus with more variables, which is what this course is about, we want to say what's the best linear approximation to a surface or a higher dimensional analog of that. So to talk about what a best linear approximation is, we need to know what linear means. And that's the reason we're doing linear algebra in this course. Most multivariable calculus courses separate them out, and it's very hard to really understand what's going on without combining the two fields together. So we're going to do linear algebra. We're going to talk about vectors, matrices, what a linear function is, and then we're going to talk about calculus for a while. So we're going to talk about limits, continuity, derivatives, and what derivatives are good for. So, what are derivatives good for? And then we're going to do more linear algebra. So we're going to talk about matrices and systems of linear equations. And then sort of the last unit of the course, and this is all at the bottom of the syllabus too, you can see that it's laid out there. The last unit of the course is basically going to be maximum problems. With applications to linear algebra. So that's more or less what the first semester is. What's missing from your prior calculus experience? Integrals, so that's second semester. So second semester we'll do a lot of stuff with integrals. We'll talk about generalizations of surfaces that are called manifolds. We'll do the theorem of calculus, which is the fundamental theorem of calculus. That'll take us about a month in the spring. It's a little more complicated in multivariable than it is in single variable. And then there'll be a bit of linear algebra that caps off the course at the end. So I'm going to try to keep the interplay between the linear algebra and calculus going back and forth through the whole year-long course. Some of you may have had a multivariable calculus course. How many? Yeah, so we have this wonderful course that people take at Tech.
Yeah.
Mine's really complicated.
Is that right?
Yep. Yep.
So generally, I will warn you guys that you probably don't know as much as you think you do, if experience is a guide, but at the very least you'll get the framework of what's going on filled in more. Okay, so I know all of you, or most of you have seen vectors before, but I'm going to assume you haven't seen vectors. And we're going to do a quick run through with what vectors are. So first of all, I want to do some notation here. So this R with an extra line in it, for those of you who've never seen it, is short for real numbers. And we all know what real numbers are, at least we know well enough that I'm not going to worry about anything more pedantic at this point. If you put a 2 up on the top of the R, what does that now represent?
Two-dimensional space.
Two-dimensional space built on real numbers. So this is going to be what people usually call the Cartesian plane. So you can think of drawing the real number line like that, and you can think of drawing the plane with 2 coordinate axes. R3, you can think of as being three-dimensional space. And usually we'll draw a 3D picture that looks something like this with the axes not exactly, they're supposed to be in some sort of perspective here. And then if you keep on going, mathematicians like to talk about things in greater generality. You put an n there, and this is now called n-dimensional space, whatever that means. And I'm going to comment that I'm using a word here that makes no sense yet, but we'll learn what it means soon. Okay, so most of you have certainly dealt with R2 because you've drawn graphs of real functions. You've drawn y equals f of x, as I did here, and this is living in R2. Not so many of you have done R3, although in your Calculus 2 course or in your BC Calculus course, you did volumes of revolution, and so you thought about chunks of space in 3 dimensions, even though the calculus was somehow one-dimensional calculus. All right, so I want some notation. I want points that live in these spaces. And so the notation for that is going to be, I'm going to write x for a vector, and I'm going to think of a vector in the plane as an arrow going from the origin to some point, and I'm going to call this arrow x, and I'm going to think of x as representing both that physical arrow and the point itself at the end of the arrow. Now the way we're going to write that is with coordinates x of 1 and x of 2, which sometimes we'll use different letters for. In 3 dimensions, I have a point in 3 dimensions that has 3 coordinates. Well, where do I see these coordinates? This is the first axis here, so this is x1 here, and this amount of the vector here in the vertical direction is x2. And similarly here, I have a vector that lives down in the first 2 coordinate plane. This is the x1, x2, and this is x3 here as an axis. And so this green vector down here, I can think of as having a part that goes in the first direction, a part that goes in the second direction, and a part that goes in the third direction. And those are the respective coordinates. So for example, if I wanted to talk about 1 to -1, I would go 1 unit in the first direction, I would go 2 units in the second direction, and I would go -1 unit down. And don't worry about trying to draw everything to scale. We're not going to, pictures are mostly meant to be illustrative and not necessarily drawn to scale. So if I take the vector in the plane that's got coordinates 1, 2, it's going to look something like that. And then I'm going to go down 1 unit from there. I can do that here, go down 1 unit there, and that's going to give me a vector like that that represents going 1, 2, and down. Okay? So vectors are important because you can think of them geometrically, but you can also think of them algebraically. And the interplay between the geometry and the algebra is going to be the major theme for the first month of the course. So here's a little bit more notation. I want to say this guy lives in the Cartesian plane. So the symbol that math people use for this is a funny little sign that looks sort of like an epsilon. Is that showing up? Can you see it? Yeah. Some people are saying no. So it's not quite an epsilon, but this means is an element to, or is an element of, or belongs to. And then we would say lives in R2. And this X, we would say lives in R3. All right, so what algebra can you do with real numbers? Surely you know some things you can do with real numbers algebraically.
You can add them.
You can add them. What else can you do?
Subtract.
Subtract.
Scalar.
You can multiply real numbers.
Divide.
You can divide sometimes.
Yeah.
So the question is, of these things you guys have just reeled off, what things make sense to do with vectors? Well, adding makes sense because you can take, if you take x and y, and I'm just going to do it in general here, but I'll draw you pictures in 2 and 3 dimensions, so you don't have to freak out about trying to draw n. We won't do that. But if you have x that has its coordinates x1 to xn, and you have y that has its coordinates y1 to yn, then their sum is defined by just adding in each slot, each component by component. Okay, so what's the geometry for that? So let's just draw 2-dimensional pictures for this. Suppose I have an x vector, and I have a y vector.
Just transpose the y vector to the end of the x vector.
Draw a parallelogram. So what Dan is suggesting is that I think about taking y, whose tail was firmly ensconced at the origin, and lifting up his tail and moving it over here, and taking a parallel copy of y, and thinking of putting it there, and then you do what?
Draw from the origin to the point
Yeah.
of y.
So you take the new head of the vector y and draw the arrow from the origin to that. Well, of course, that's what these pictures are saying, because if you think about taking y and thinking of him as a little triangle here, I've transported that triangle over there. And so to the x coordinate to the first coordinate of x, I've now added the first coordinate of y. And to the second coordinate of x, I've now added the second coordinate of y. So adding those two gives me this height. Adding these two gives me this horizontal displacement. So that's the picture that you're allowing yourself to move y parallel to itself and slide it over there and think of that. So that's a nice picture. Okay. What about subtraction? What does subtraction mean? Adding the additive inverse. I knew you'd say that. So what is the additive inverse anyway?
X something or
Ooh, that's a theorem.
what you can add to a number to get 0.
So if you had a real number A, you would say, what number can I add to it that gives me back 0? So in our case, what's the 0 vector, by the way? I didn't say that explicitly. Well, it's the 0 vector. They don't make chalk the way they used to. It's not just cars. So the 0 vector has all its coordinates being 0, so if you take the arrow from the origin to it, it doesn't go anywhere. It's just sitting at the origin. So the additive inverse of a real number is the number which, when added, gives you back 0. You think about that in terms of directed distances on the number line, something like that. Go a units to the right, then negative a should be a units to the left, and adding those, you go here and you come back, you're at 0. Okay. Matt's saying that there's a theorem that taking the additive inverse of a is actually the same as taking -1 times a. I think that's actually one of your extra credit problems to do on the first homework assignment. There's another interpretation of subtraction. Go back to middle school. Before you learned about additive inverses, you learned how to do subtraction. I guarantee you. Well, maybe I better not guarantee. Yes, sir?
Counting backwards by the numbers?
That's sort of doing this, though, isn't it? So if I asked you what's 5 minus 2, you're saying go 5 units, count back 2. So you're adding the additive inverse of 2.
Okay.
But there's another way of thinking about this where you don't have to think about inverses.
It's what you need to get from 2 to 5.
Right. This is asking the question, if Johnny has 5 apples and mean Gale takes away 2 of them, how many does Johnny have left? Well, the number that he has left plus those 2 that Gale stole would give Johnny's original 5. So you're asking the question, by the way, this is the math symbol for equivalence, or if and only if. Usually it's written this way, but you'll find that I write it in all sorts of orientations. It's okay. So this is officially how you write if and only if. This part is implies, and this part is
Implies.
implies the other way, which is,
One implies one, the other one
so
implies.
if you write P implies Q, that means if P is true, then Q follows. And if you put P here and Q there, that means Q implies P, which means if Q holds, then P has to hold. So some people will call that just if. And then this direction is the only if. P holds, Q holds only if P holds. But never mind. I got off track. 2 plus what gives me 5. All right, that's really the way you should think about subtraction. So now that I've said that, tell me how to subtract vectors.
You want to get from the end of one to the end of the other by using a vector.
So some of you are going to go back to this additive inverse stuff and tell me that if I start with x and y, I could imagine an additive inverse for y, which would go like this. And I could imagine adding that to x. And I would get, running out of colors here, I would get x plus negative y. But I'm suggesting there's a better way to think about it. Yeah?
Taking the vector from the head of y to x and then transposing that onto.
Exactly right. So if you think about what I was saying here, you're saying x minus y is the vector which, when added to y,
It's to x.
gives you x. So I say to myself, here's y. What do I have to add to y to get to x? And that's the difference. So x plus, y plus the difference gives me x. And so this is the way, if you've done physics, this is the way you always think about subtraction in physics. You want to think about if the current of the river is flowing with velocity vector y and I want a resultant vector of x,
How fast you have to go.
how do I have to row my boat? And the answer is, that's what you have to do to end up with x. So that's really the way you should think about subtraction. Now, every year I make a big deal about this, and I say, you're going to poke fun at me for taking you back to 5th grade, but every year people screw up and get the arrow going backwards on this. So don't do that. If you think through this way, you'll always get the arrow pointing in the correct direction. I mean, you're safe to do it this way, but it's easier to just look at it this way and say, okay, I'm at y, how do I get x? Okay, so that's subtraction. And I didn't write down the algebra, but obviously you do the subtraction component by component. Okay, a few other things you can do with vectors. What other algebra could we do? Well, we talked about multiplying real numbers. So I don't know how to multiply two vectors, but I do know how to stretch a vector. So if you have a real number, c, and this is often called a scalar, for reasons that will become obvious in a second here. If you have a scalar c, and you have a vector x, you can scale x by a factor of c, where you just multiply each of its coordinates by the scalar c. So what is that doing geometrically? Well, that's pretty easy. If you take x and you double each of his coordinates, then it won't take much imagination to realize that you've got a vector twice as long in the same direction. And if you did negative numbers, what happens then?
You have to reflect it.
Yeah, you reflect through the origin, you go in the other direction. This would be approximately negative 1/2 times x, something like that. Okay. Well, there's a very important notion that to each vector, there's a notion of its length. So if you go back to the beginning picture here, if this is x, how long do you think it is?
Square root of the sum of the squares of all.
Square root of the sum of the squares, right? That's called
Pythagorean.
Pythagorean theorem. So in R2, you're going to have that the length of the hypotenuse squared is the sum of the squares of the legs. So you could say that the length is the square root thereof. Why does that work in 3 dimensions?
Because the x, the
You can do it.
vector squared already has the first two component squares if you add them all together.
Yeah, you can do it stepwise. So you can do a 2-dimensional vector in the bottom plane and then do the
There you go.
vertical.
So you can
component.
think about this triangle here, and that is a right angle, because if you're a vector living in this plane and you go vertically up, that's a right angle. So you have a right triangle here where we've already now established that this length is the square root of the sum of the squares of the first two coordinates. This is now x3, so you have this right triangle. The hypotenuse is you get the square of the part in the base plus the vertical part squared. And that, of course, is now the sum of the squares. Everyone okay? So in general, if x is a vector in Rn, define the length to be the square root of the sum of all the squares. That's a definition, but presumably what I've said makes you believe that it's a meaningful one that generalizes what you already know. You okay? Well, sometimes it's important to think about two directions being in this, two vectors being in the same direction, but they might have different lengths. So, for example, if you had x here and y here, you could convince yourself that y is a rescaled version of x. So, definition, we say x and y, two vectors in Rn, are parallel. Now remember that we're thinking of these both as vectors with their tails at the origin. I'm not sliding them around, but we're just saying two vectors with their tails at the origin are parallel if one is a scalar multiple of the other. And one thing I am going to teach you to be careful about in this class is how you use the English words. So it's important to say, for some scalar, this happens. Or if the other one holds. Of course, they won't be the same C. They'll be different scalars. But why am I saying both?
Yeah, because couldn't C be also like a fraction of a number?
Sure.
So why would you need both statements?
Right. My question exactly.
Oh, sorry.
No, you're fine. So what we're saying here is if y is 5x, then x is 1/5 of y. Why did I bother with both of these?
If one
Because
is
of the
a zero vector, then you're running into a problem.
Yeah. So different books handle this different ways, and I never remember how I handled it when I wrote the book, so I have to always look every time I teach this class and remind myself. If one of these vectors is 0, it's parallel to anybody.
Right.
Because so this is a fact, which again is part of that challenge problem for homework. If you take 0 times any vector x, you always get the 0 vector. It's not an axiom for vectors, it's actually a theorem, again, very much related to the one Irby mentioned earlier about the additive inverse being -1 times. So this tells you that the 0 vector is parallel to any vector x. But if I wrote, if y were 0 here, this would hold, right? 0 is c times x, where c is the 0 scalar. But can I go the other way around?
You have to multiply
No.
by infinity.
I don't have a way to cancel out a 0. From the 0 vector, I can't recreate a non-zero vector x. So that's why there's this silliness in this definition. We're allowing 0 to be parallel to other vectors. But if you look at most linear algebra books, they will only talk about non-zero vectors here, and so they don't have to deal with this nonsense. Well, a convenient thing to do is to take a vector and scale it so that it has length 1. Of course, if you started with 0, you couldn't do that. But here's a fact for you that is useful. If you take a scalar times x, what's the length of that?
Scalar.
The scalar times
times
the
magnitude.
legs.
Good, you fell in my trap. How many vote yes? Oh, don't be intimidated.
Too late.
How many vote no?
That would have to have
So when I said you fell in my trap, you need absolute values there. Why?
Because the magnitudes are squares.
Negative length.
Lengths are always positive, or 0.
So it could be negative.
And if you took a negative scalar, obviously if you took negative 2x, it's still got the same length as 2x does. So you need the absolute value of the scalar. Where does that come out from this formula?
You're squaring all the numbers so the negatives go away.
Go on.
If you have a vector with a negative component, which all vectors with a negative,
Yeah, so if all these c's were negative, and you square a negative,
it becomes a
and
positive.
you take the square root, what do you get?
Positive.
What's that called?
The absolute value.
Alright, that's where the absolute value comes from. Okay, so definition, we say x is a unit vector if it's got length 1. Magnitude of x is 1. And then if I took any vector, for example, the vector 1, 2, 3, what length does it have?
Yeah.
This is hard. Square root of 1 plus 4 plus 9, 14. So this vector has length square root of 14. So here I have a vector, I'm not pretending it's drawn to scale. It's got length square root of 14. How can I find a unit vector that's parallel to it?
You could
Divided by.
So if I took 1 over the length
times the vector itself.
times the vector itself, that vector would now have length 1. So that's called normalizing the vector, where you turn it into a parallel unit vector. Okay, so what we'll do tomorrow, remember at 11 o'clock tomorrow, we'll actually start to do some proofs using this vector algebra versus geometry. So I'll remind you about some basic high school geometry stuff that some of you never knew. And then we're going to work our way on to talking about dot products. I will be in my office this afternoon if you need me. Make sure I get the class list back. Did you get it?